Welcome to Brain Vision.
The first step to doing this problem is to figure out what is actually happening. Originally, we have a rocket on the ground floor, and it's boosted up by a constant acceleration of 2.25 meters per second squared until it reaches a point where the engines brake at 525 meters up. And then it's only affected by the acceleration due to gravity, negative 9.8, until it reaches a maximum height and then drifts back down to the ocean ground, or to the Earth's ground. Now, the first step to solving part A is to figure out what velocity it is at this level here. To do that, we use kinematic equation 3 here, because we know that v naught is equal to 0. So v squared is equal to 2a x minus x naught. We know a is 2.25 meters per second squared, and x minus x naught is 525 meters. Plugging that in, we get that v is equal to 48.6 meters per second. Now that we know the velocity at the point where the engines brake, we need to figure out the time it takes for the rocket to get to its maximum height. To do that, we use kinematic equation 1, which is v equals v naught plus a times t. In this case, a is equal to negative 9.8, t is our unknown, and then v minus v naught is 0 for v, because at the maximum height, v will be 0, and then v naught is actually this value. And so we get negative 48.6 is equal to negative 9.8 times t. So t is equal to 4.96 seconds. Now to get the x value here, we can use kinematic equation 2. So x minus x naught, where x naught is 525 meters, is equal to v naught, and in this case v naught is 48.6 times t, 4.96, plus 1/2, negative 9.8, 4.96 squared. Solving this for x, we get that x is equal to 120.51 meters. That is the x in between the maximum height and when the engines brake. But so it's not the maximum height. To get the maximum height, we have to take this value and add it to the 525. And so we get 645.51 for the maximum height. And that's the answer to part A. For part B, we need to figure out the time it takes for the rocket to reach all the way back down to the ground and the velocity that it is at that point. So let's look at this a little further. We know that the time it takes the rocket to get from here to the X is 4.96 seconds. Which also means it takes 4.96 seconds for it to fall back down to this height here. We also need the time it took the rocket to get from the ground floor initially up to a height of 525. And so for this, we can use kinematic equation 1. And so this time here, the final velocity is 48.6. And it's equal to 2.25, because that's the acceleration, times t. That yields a t value of 21.6 seconds. And so it takes 21.6 seconds for the rocket to get initially to a height of 525 meters. It takes 4.96 to go up till it's at rest, and then 4.96 to go back down. And so lastly, we need the time it takes to get from 525 down to 0 again. And so it's actually easiest to calculate the final velocity at this point, and then we can use that to find the time it takes to get to that point. To find the final velocity at this point, we're going to use kinematic equation 3 again. And so I'm going to go to a new sheet here. And using kinematic equation 3, I get that v squared is equal to 2,362 plus 10,290. And I got that from using this. V naught is negative 48.6 at this point after it falls down. A is still negative 9.8, and then x minus x naught is negative 525. And then whenever you plug those numbers in, you get these. And then you add those together and take the square root, and you get that v is equal to negative 112.5. When you take the positive square root, you won't get a negative here. But we know that since the rocket is moving down, it must have a negative sign. So we can take the negative square root of this, and that's what we should do. This is in meters per second, by the way. Now that we have the velocity that the rocket has when it reaches the ground, we can figure out the time it takes for it to go from here down to here. And to do that, we can use, I believe, kinematic equation 1 again. So I get v minus v naught is equal to negative 9.8 times time. And then v minus v naught, plugging that in, and then solving for t, we get that t is equal to 6.52 seconds. And so it takes 6.52 seconds to make this trip. The total time is the sum of all the individual times. We know that it takes, where's it at? Here it is, 21.6 seconds to go from here to here. So 21.6 plus 2 times 4.96. 4.96 seconds up, and then 4.96 seconds down. And then we add that to the last bit, 6.52. When we do that, we get 38.04 seconds for the total time. On to part C. It's easiest to start with the acceleration, since acceleration graphs tend to be simpler than velocity or position graphs. So if I start with a y here and t on the x-axis, we know for the first bit of journey up until the engine's brake, it is at a constant acceleration of 2.25. At this point, the engine's brake, and it goes all the way down to negative 9.8, because that's the acceleration at that point. And my pen's glitching out. I think I got it now. Yep, okay. Negative 9.8. By the way, this t value is 21.6 seconds, since that is the time it takes until the engine's brake. And so that's what the acceleration graph looks like. To do the velocity graph, oh, pen's glitching out again. To do the velocity graph, we need to essentially integrate the acceleration. In this case, since the acceleration is just a constant value, the velocity is going to be a linear line. And since the acceleration is positive, it's going to have a positive slope here. It's going to start at 0 since the initial velocity was 0. And it's going to go until the engine's brake. And the engine's brake velocity is 48.6 meters per second. At this point, the velocity is no longer going to be increasing because the acceleration is now negative. And so if you integrate this constant, you get another linear line, except it goes negative. And I didn't really space this right, but I think you get the idea. This is, or I keep labeling it y. It should be t. That's the time. The time it takes for the full journey is 38 seconds, so I'm going to put that there. The time where the engine's brake is 21.6 seconds, and the velocity at the end, we calculated in part B, and it is negative 112 meters per second. So the velocity looks kind of like that. The position, I'm going to try and squeeze it in here. It's just the integral of the velocity. And so since we have a line here, a linear line with positive slope, I'm going to have a parabola here up until the engines break, which is, say, there at 21.6 seconds. Should label this t, and then this is y. At this point, since velocity is now a negative slope, we have to curve this back down. This makes sense with our intuition. The rocket initially is being boosted up, and then once the engines break, it goes up a little more because of its initial velocity, and then it crashes back down to Earth. The time at which it crashes back down to Earth, we've already calculated. It's 38 seconds. And I think that's it. This maximum height we calculated in part A as 645. So that's the y value there, 645 meters. And so I think that's the end of the problem.